So here we have molecules, molecular formulae, empirical formulae. And so it was suggested in chat that empirical formula is simplified. Yes, it is the, oopsie, lowest whole number ratio, or the simplified version of atoms in a molecule. So then what's the molecular formula? It's the actual number of all the atoms of every element in a molecule. So it is the actual number, the total number of all atoms of each element in a molecule. So the molecular formula is going to count everything. If this guy has 2 carbons, we're going to put 2 carbons. If this guy has 1, 2, 3, 4, 5, 6 hydrogens, we're going to put 6 hydrogens. But notice that 2 and 6 are both divisible by 2. So I can divide both by 2 and get my empirical simplified reduced ratio formula, C1H3. Good? Easy peasy, right? Count atoms, get the molecular formula. Reduce to simplest terms, find the empirical formula. So what would be the empirical formula of dinitrogen tetroxide? What would be the empirical formula? What do you think? Exactly, just NO2. You can divide everything by 2, N1O2. You can draw the 1 if you want to, but you can also leave it invisible. Chemists do love their invisible ones. So this would be the empirical formula. How about sulfur hexafluoride? You're going to have to write that formula first. Sulfur hexafluoride. How many fluorines in hexa? 6. Good. I have S1F6. What is going to be the empirical formula? Can I divide both by 2? No. Nope. Yeah, so sometimes the empirical formula and the molecular formula are the same. So this guy cannot be reduced. The empirical formula is the molecular formula. How about this guy? So each of the black atoms is a carbon, and each of the white atoms is a hydrogen. So what is going to be the empirical formula of this guy? Good, good. C4H9 is the empirical formula because the molecular formula was C8H18. Anybody know what that's called? What is this molecule, this compound? You have 8 carbons in a hydrocarbon. We find it in gasoline. What's our prefix for 8? So not octane. Yeah, this is octane. The 8, exactly. Exactly. Good. All right. So now we're going to go back and review percent composition a little bit. Remind me about percent composition. How do we find percent composition? How do we find that? What was our little formula for percent? Perfect. Part over whole times 100. Brilliant. So we're going to do the part that's carbon divided by the whole that's methane, CH4. So carbon is 12.011, hydrogen is 1.01, but there's, sorry, 0.08, but there's 4 of them, so that's going to be 4.032 total. And then if I add the 1 carbon and the 4 hydrogens, 12.011 plus 4 times 1.008, it's going to give us a grand total of 16.043 grams per mole. So the part that's carbon, 12.011, divided by the whole, 16.043 times 100, is going to give us 12.011 divided by 16.043, 74.9% carbon. Do the same thing for hydrogen. Take the 4.032 divided by 16.043 times 100. 4.032 divided by 16.043 times 100, 25.1% hydrogen. Good. So part that's 1 element divided by the whole mass of the whole compound times 100 will give us our percent composition. When we figure out the empirical formula from data, sometimes I don't have a picture or a molecular formula. Sometimes we just have data. Sometimes we have percent composition is our data. We're going to just do this backwards. So here, I took mass divided by mass times 100 to get to percent. Here, I'm going to turn my percents back into moles. And turn my percents into moles. So what we're going to do is we're going to take our 75% carbon, and instead of thinking about it in terms of percent, I'm going to think about it in terms of grams. Because if I had 100 grams of this compound, and 75% of it was carbon, that would be 75 grams. We just pretend like we have 100. So 75% of 100 is 75 grams of carbon. I'm going to turn that into moles with my 12.011 grams per mole. 75 divided by 12.011. 75 divided by 12.011 is going to give us 6.24 carbons. We're going to do the same thing for the hydrogen now. We're going to take that percent composition and go backwards, use the mass to turn it into moles. So if I have 25% of 100 is hydrogen, I'm just going to turn that into a gram. 25 grams of hydrogen, use the molar mass of hydrogen to figure out how many moles of hydrogen we have. 25 divided by 1.008 is going to give us 24.80 moles of hydrogen. So now I can write a formula. I know that our mole numbers are also the subscripts in our formula. So I can write a formula, C, 6.24, H, 24.80. And tell me how much that looks like every chemical formula that we use. 0 it looks like, because we never put decimals in our formulae. So how could I scale up these numbers to whole ratios? Scale up or scale down? So we could round, but I think 2, 4, and 0.8, that's a lot to round. What if we divided both by the smaller of the two? If I divide 6.24 by 6.24, I'm going to get a whole number, right? What will we get? What will that whole number be? 1. Here comes the magic. Are you ready for this? What if I divide 24.8 by 6.24? 24.8 divided by 6.24. 3.97. Round that 7, that 9 is going to turn that 3 into a 4. My friends, look. We just went backwards. We found our CH4. We totally just found CH4. So what we do is this. We take our percent and pretend like it's a gram. We just decide that we have 100 grams of stuff. Turn our grams into moles. That mole number becomes the subscript in the formula. But then to get rid of all those ugly decimals, we're going to divide everything by the smallest. 6.24 is the smallest. Divide everything by 6.24. That turns this guy into a 1, and then this guy rounded to a 4. Let's do another one. We have 25 grams of sulfur and 25 grams of oxygen. I need to figure out the empirical formula. What should I do first? What should we do? Turn our grams into moles. We're going to turn our grams into moles. So 25 grams of sulfur. We're going to turn those grams of sulfur into moles. Find the handy-dandy periodic table. Sulfur is 32.066 grams per mole. And we put grams on the bottom so that it cancels out with those grams, right? 25 divided by 32.066 is going to give us 0.7796. We're going to leave it like that for now. You can keep as many decimal places as you want to because we're going to divide in a second anyhow. So that's our sulfur. Same thing for our oxygen. 25 grams of oxygen. Now this is not oxygen gas. This is oxygen in a compound. If we're talking about oxygen in a compounds, we're not talking about it needs to be diatomic. So for these guys, don't think O2, just think how much O is in this compound. So I'm going to use 15.999 grams in 1 mole of oxygen. We put the grams on the bottom so that grams on the top and on the bottom cancel out. What we're left with, 25.00 times 1 divided by 15.999, we get 1.563 oxygen. So I can write a formula. Sulfur, 0.7796. Oxygen, 1.563. What should I do now? Because that does not look like a healthy formula yet. Divide by the smaller. Which one is smaller? Divide both by 0.7796. That's an easy one for sulfur. It's just a 1. What do we get for oxygen? 1.563 divided by 0.7796. 2-ish. Voila, SO2. Good? Not terrible, right? Yeah, that's the magic of practice. The more we do, the more it makes sense. So as tedious as practice feels, I promise this unit, especially the more we practice, the more sense it makes. All right, let's do another one, talking about practicing lots. How about if sorry? A different percentage. I'm thinking about, what if I don't do this one and I put 3 minutes on the timer and you do it on your own and then we check in a couple of minutes. Good? Good. All right. So 3 minutes on the timer. Go. All right, that was time. Hopefully you turned your grams of phosphorus into moles of phosphorus, found about 1.4, keep some decimal places. Same thing for oxygen, 3.5, keep some decimal places. Divide both by the smaller, I got 1 phosphorus, 2.5 oxygen. Can I just round that to 3? Sure. That's a whole half an atom. Like 0.98. We can totally round that. But a whole half an atom? Just be like, meh, close enough, call it another half an atom? Oh no. What might be a better empirical formula? Instead of rounding to 3, what if I multiplied both of them by 2? What if I got P2O5? Maybe that's better than rounding away a whole half an atom? What if we had done this and I got P.301? Then I should multiply both by, maybe not 10. Yeah, if I multiply both by 3, that 1/3 will turn into a 1. What if I got P101.25? What could I multiply to get rid of 0.25? 4. By 4. P4O5. So, my friends, there's a little bit of gray logic involved at the end of this. If you get P104.9998, yeah, you just round that to 5. But 2.5, a 0.3, a 0.25, that's a lot to round away. So definitely think about what scale factors you can use to get things to a whole number. Good-ish? Sure. All right. Just an FYI, for us this year, I will never give you a 0.3 or a 0.25. It'll be either obviously just round or it'll be a half and you'll note a double. Good? Good. All right. So we just figured out that this was P2O5. This is the same data that we had on the last screen. We decided that P2O5 was the empirical formula. Now we're going to add a new layer and figure out the molecular formula. How we do that is we'll be given the molar mass of the compound. So I know that the reduced form is P2O5. If I add 2 P's, 2 times 30.947, and 5 oxygens, 15.999, I get a mass of 2 times 30.974 plus 5 times 15.999. So I should have a molar mass of 141.943 grams per mole. That's what it is according to P2O5. But the question tells me that it's 283. So it's twice as big. The molecular formula is twice as big. If I do 283.88 divided by 141.943, we get a scale factor of just about 2. So what should I do with that 2 and my P2O5? We're going to multiply. We're actually going to go ahead and distribute that 2. So because 2 P2O5 is not a molecular formula. To turn it into a molecular formula, we do have to count all of the atoms. It's going to be P4O10. So that'll be our molecular formula, which makes sense because if I divide both of those by 2, I get our empirical formula. How are we feeling? Still making sense? Yeah, good. All right, let's do this one. So nicotine, which is in tobacco plants, the stimulant in tobacco, is carbon, hydrogen, and nitrogen. So let's figure out the empirical formula from all that data. So we're going to turn our carbon into grams. Good. We're going to do that by using the molar mass of carbon. Carbon's 12.011 grams per mole. There's our carbon. Do the same thing for hydrogen and nitrogen. Good. Now what do? Divide by the smallest. Perfect. What's the smallest? Good. 1.233. So nitrogen's an easy one. That turns into a 1. Carbon 6.164 divided by 1.233. 4.999. Can I call that a 5? For sure. How about hydrogen? 8.631 divided by 1.233. Ooh, I got exactly 7. Not even any rounding necessary. So this is our empirical formula. C5H7N. Good? Guess what we're going to have to do next? Molecular formula. So C5H7N1 is what we just found. That's the empirical formula. We're told that the molar mass is 163.23 grams per mole. So how can I use that information and the empirical formula that I just found to figure out the molecular formula? What should I do? Add up what? Exactly. We're going to find the mass of the empirical formula. So we're going to do 5 times carbon plus 7 times hydrogen plus 1 times nitrogen. We're going to find the mass of the empirical formula. 5 times 12.011 plus 7 times 1.008 plus 1 times 14.007. I get 81.118. Now what? Divide. Yep. Perfect. So we're going to divide the molecular mass, 163.23, divided by the empirical mass, 81.118. Looks like 2. So this is basically our scale factor to get to the molecular formula. So what should I do with that 2? Exactly, multiply everything in the empirical formula by that scale factor of 2. So nicotine's molecular formula, there are 10 carbons, 14 hydrogens, and 2 nitrogens. Voila! Easy peasy? Or not terrible? Not terrible? I'll take a not terrible. All right, so remind me, what steps do we follow? What steps did we follow to find empirical formula? First, what do? Good. So if you have percentages, turn your percentages into grams. If you have grams, you're good to go. So percents to grams, and then grams to moles. Good. So to find moles of each element, that's basically the subscript of your formula, but it's usually not a whole number. So how do I scale to whole numbers? Divide all the mole numbers by, good. And then watch your rounding. If it's a 0.5, make sure that you adjust for that 0.5. Good? How do I find the molecular formula? What should we do first? Think about here, what did we do? Good. We're going to add together all the atoms of the empirical formula. We're going to find the mass of the empirical formula. Then we're going to divide that bigger molecular mass by the empirical mass that we just found. That's going to give us a scale factor. What are we going to do with that scale factor? We're going to multiply all the subscripts in the empirical formula by that scale factor. Good? Questions? We finished early. I'm not sure what to do with us today. We finished early. You have to start the homework early. Yay, homework. Homework is published at 5.2. I'm going to publish it right now. If you got a copy of the study guide, it's in the study guide if you want to start it on paper. If you don't need the paper, you can go straight to Canvas. Make sure that you're also thinking about your mole project. Pick a problem from that list in Google Sheets and then just do some fun, strange math. Write that reflection on working in a group. And then, oops, that says Tuesday. It should be Monday. I still haven't quite adjusted all our days from last week's snow. Another quiz on Monday at 1:45. So 1:45, you do not have to come to Zoom unless you have questions. 1:45 to 2 on Monday will be quiz time. And then we'll start talking about more stoichiometry at 2 o'clock on Monday. Questions?